In my last class, I talked about the eightfold wave and the basic quark model, and now in this class, I'll be talking about the hadrons in the UD sector. That means those baryons and mesons which contain only U and D quarks. And in the next lecture, I'll be talking about hadrons in the UDS sector. That means I'll be talking about hadrons which consists of all three of them together. And through this lecture, we particularly aim to construct not only the baryon flavour-spin state function, but also you see this pion flavor state function for this UD sector. Now in my last class, I already talked about that Gell-Mann and Zweig observed the familiarity of the eightfold pattern with the SU2 and SU3 group symmetry group, and using these ideas we are finally able to construct the wave function as well. But first let me very briefly talk to you about these symmetry groups. Now you see the unitary group UN is a group of unitary complex square matrices with n rows and n columns. A complex n by n matrix has 2n square parameters, we know that. But the unitary condition, which is this, imposes n square constraints, and thus the total number of free parameters is n square only. A particularly important group is the group U1, which has just one free parameter and so one generator. This corresponds to a phase transformation. You see this U exponential I by h cross alpha A, where A is the Hermitian operator and alpha is a real number. Now the relevant case here being A being the identity operator, like a global change of the phase of the wave function as discussed above, or an operator associated to a single measurable quantity like the electric charge or the baryonic number. Now Noether's theorem ensures that the invariance of the Hamiltonian with respect to such a transformation entails the conservation of a corresponding measurable quantity. The special unitary group now from UN to SUN. The special unitary group SUN, what's so special? You see, is a group of unitary complex matrices of dimension n by n. Up to this part, it's the same as the previous one, but now with this one new addition, with determinant equal to 1. And so the number of free parameters and generators of this group is thus n square minus 1, since the determinant must be equal to 1. Particularly important groups will be the group SU2 and SU3. Now, so you see, first one is SU2, which we will talk to you about in this lecture. The symmetry group of isospin is the group SU2, that is two-dimensional unitary matrices group. This group has infinitely many representations, singlets, doublets, triplets, etc. Here I have just written down the three generators of this isospin group, which are the three Pauli matrices. Now these Pauli matrices, sigma 1, sigma 2, sigma 3, have the following properties, which I have again written down here in this form. The third Pauli matrix, important to note, is diagonal. The rank of a unitary group is given by the number of the diagonal matrices. So, in this case, the group SU2 has rank 1. The commutation relations of the Pauli matrices define the Lie algebra of the group SU2. This is the thing here. So you see, an isospin representation of isospin T has 2T plus 1 different states, which has different values for the third component of the isospin. For example, the nucleon, which is an isospin doublet having T is equal to half, so Tz will be plus half and minus half, the two components, proton and neutron. Similarly, the 3 pi mesons form a triplet, T equal to 1 or Tz equal to 0, plus 1 and minus 1. And we can similarly move forward to the case of delta resonances, which is an isospin quadruplet. T is equal to 3 by 2. And so, Tz components will be plus 3 by 2, plus half, minus half, and minus 3 by 2. So, with these basic ideas, let me now move forward to the Isospin and Flavour symmetry, the basic introduction to the mathematics of them. You see, the proton and neutron have very similar masses, and the nuclear force is found to be approximately charge independent, which means the force between two protons is approximately equal to neutron proton, and again this is approximately equal to 2 neutrons. And to reflect this symmetry, Heisenberg in 1932 proposed that if you could switch off the electric charge of the proton, then there will be no way to distinguish between a proton and a neutron. And thus we have the nucleon, which has 2 states, proton and a neutron. And so we have this simple way of representing the proton and neutron by a 2-column matrix 1 0 0 1, which is very much analogous to the spin up and spin down states of a spin half particle. Now, regarding spin, it is important to note that just as angular momentum conservation comes from rotational invariance in real space, so isospin conservation comes from isospin invariance in charge or isospin space. Now the rotational transformations in either real or isospin space form a group which is the same. That means the SU2 group. Now in case of this isospin conservation, what happens is that suppose we make a transformation of a nucleus of A nucleons having Z protons. So how many number of neutrons are there? A minus Z. Now under this isospin transformation, the nucleus will be converted to another one which have the same A nucleons but Z prime protons, and so A minus Z prime neutrons. Note that there is no change in its properties so far as the strong interactions are concerned. And this is what is meant by isospin invariance or rotational invariance in isospin space. Thus, we expect the physics to be invariant under the rotations in this space. And as I have already mentioned, the neutron and proton form the isospin doublet with total isospin I equal to plus half and the third component I3 is equal to plus minus half. Now, as I have already mentioned to you in my previous class also, proton has component UUD, neutron has UDD. So basically the isospin invariance is reflected by is there because of the flavor symmetry. That means same mass and other properties except the charge. That means for these 2 U and for these 2 quarks, that means U and D quarks, apart from the electromagnetic effects, they have the same mass and all other interactions. But this is not actually correct, since there is a difference in mass between the U quark and the d quark of the order of 2 to 3 MeV. So we have an approximate flavor symmetry in this scenario. But still, we will move with this idea of approximate flavor symmetry and see what do we get. Here you see the baryon decouplet, which I have already discussed to you about in my last class, and I have also mentioned that this we have an inverted triangle like figure, but I have not shown the mass of the various particles here, and here you can see the masses of the various particles. So interestingly, you see they have an average mass of this delta particles of 1232 MeV. Now you see the average masses I have denoted here, as I have also talked before. The question is, why are they not these masses all the same? Well, this is because we have UDS quarks in this scenario. But what about this case? They have the same UD composition, right? And so the reason that the masses are somewhat different from each other is because of this somewhat approximate flavor symmetry. That means if the U and D masses were all the same, then these all particles will have same mass. All particles of a multiplet will have the same mass. But this is not so, because we have a case of somewhat broken symmetry. Fine. So now let me move forward with the flavor symmetry idea. You see, let us now extend this idea forward. As I've already mentioned before, we have a case of approximate flavor symmetry. So, which means that from the point of view of the strong interaction, nothing really changes if all the up quarks are replaced by down quarks, and so on and so forth. Let us now choose these two column matrices 1 0 and 0 1 for the U and D. Similarly, we can express the invariance of the strong interaction under this UD symmetry as the invariance under rotations in the abstract isospin space through this U prime D prime U UD. Here, this 2 by 2 unitary matrix depends on 4 complex numbers, which means 8 real parameters. But there are also 4 constraints from this unitary condition, and as a result we have 4 independent matrices. Thus, in the language of group theory, the 4 matrices form the U2 group. Fine. One of the matrices corresponds to multiplying by a phase factor like this through the identity matrix, which is not a flavor transformation and of no relevance here. The remaining 3 matrices form the SU2 group, special unitary condition, with determinant of U being equal to 1. Fine. Now for an infinitesimal transformation in terms of the Hermitian operator G, you can write U as like this, and if you demand the determinant of U to be equal to 1, we get trace of G equal to 0. So a linear independent choice of G are the spin matrices, Pauli spin matrices. These are written here. The proposed flavor symmetry of the strong interaction has the same transformation properties as spin. You see, sometimes you might find that I am repeating the same things. This is also to point out the relevance and the importance of what we are learning here. Okay, so let us now define isospin T as half of this sigma and U being equal to e to the power I alpha dot T. Now you can check for yourself this for the case of an infinitesimal transformation here. Okay, having a unit determinant. Now the properties of isospin. It has the same properties as the spin, which works, right? You see this thing, we all know that. We are quite conversant with the spin scenario. As in the case of spin, we have three non-commuting operators, T1, T2, T3, and even though all three correspond to observables, we can't know them simultaneously. So the level states in terms of total isospin I and the third component of isospin I3. And again, the eigenstates are exact analogues of the eigenstates of ordinary angular momentum. You see this thing, analogy. And so I have again written this analogy here like this. And here, this is a very interesting one-dimensional plot in I3 axis, where I have shown the U and D quarks in terms of I3 assignment. Now, let us define the isospin ladder operators, which are quite analogous to the spin ladder operators. You see T plus and T minus. T minus converts from U to D and T plus to D to U. Why? Because you see this is the number. T has minus half and U has plus half. Now this is just an assignment. We start with this idea. And as a result, you see this is the operator. Now this step up or down in I3 until reach the end of multiplet. So you see the end ones have this property, this thing. Now the ladder operators turn U to D and D to U as I have shown here. Now this combination of isospin, that is the isospin of a system of two D quarks, is exactly analogous to the combination of a spin. The same scenario. So in strong interaction, I3 and I are conserved, quite analogous to the conservation of Jz and J for angular momentum. And now we move forward to our main motivation, which is the derivation of proton, neutron and delta plus wave function, or flavour-spin state function. Fine. So the first thing to do is we have to combine quarks. Till now we have been talking about only one quark, and now I'm going to talk about two quarks. So let's first combine two quarks and then afterwards combine the third one and use the requirement that fermion wave functions are antisymmetric. So these are the basic ideas. So here I have done the simple mathematics. Note that this symbol represents two states with the same value of I3 here. So this means there are two states, UD and DU. And we can immediately identify the extremes, you see, this way, UU and DD. These are the cases. And to obtain the 1,0 state, we use the ladder operator like this. And so the final state 0, 0 can be found from orthogonality here. So from 4 possible combinations of isospin doublets, we obtain a triplet isospin 1 state and a singlet isospin 0 state. Okay. The circle along the symbols, this one here, indicate that these are not just normal numbers, but we are dealing with groups. So this is important. This is the first thing we obtain after combining two quarks. And I will again repeat this when we talk about the mesons later. Now we can move around within the multiplets using the ladder operator. The states with different total isospin are physically different. It is important to note this. So the isospin 1 triplet is symmetric under exchange of quarks 1 and 2 whereas the singlet is antisymmetry. So what to do next? Very simple. Now we add up one additional quark, and from each of the 4 states, 1, 2, 3, 4, we get 2 new isospin states with this, and the result is this. You see, this jungle of states. But it's very simple if you come from here to here. So we have to just use the ladder operator and orthogonality to group the 6 states into isospin multiplets. Now let's start with the DDD. Here, let's derive the 3 states, I is equal to 3 by 2 states from the DDD state here. So we start with the one extreme, most extreme state here, which means this one, and just using the various ladder operator, we will make the other states. So that's the basic idea. You start with the one extreme and then use simple mathematics and you construct the other ones. Okay, and here the various steps I have shown this thing here. 3 by 2 minus half, 3 by 2 plus half, 3 by 2 plus 3 by 2. Of course, this DDD is 3 by 2 minus 3 by 2. Thus, from the 6 states of previous page, we use orthogonality to find these states. And from the 2 states on the previous page, we get another half plus minus half doublet. And thus, the 8 states, these are the various 8 states, are grouped into an isospin quadruplet and 2 isospin doublets, like this, here, 4, 2, 2. Direct product, direct sum. Now the different multiplets have different symmetry properties, which I have also shown here. This quadruplet of states are symmetric under the exchange of any 2 quarks, whereas these 2, they have mixed symmetry, which means they are symmetric under 1, 2. Whereas this one is mixed antisymmetry for 1, 2. Fine. Now, let us introduce the concept of spin. So far we are talking about flavor only, but we know that isospin and spin are very similar to each other. So we will get the exact same result if we consider spin also. And so you see this thing and this thing, they are the same. Fine. Now let us write down the total wave function for the case of 3 quarks. So baryon wave function for the UD sector. That means those baryons which consist of only U and D. Now, so we start with the total wave function, which we have expressed here as the product of 4 cases, right? 4 separate wave functions: flavor part, spin part, color part, and the space part. Now the color wave functions for all the bound QQ quarks is antisymmetric. And also in this case right now we will consider only the lowest mass ground state baryons, but there is no internal orbital angular momentum. That means L is equal to 0. And what does this do? This means that the spatial part is symmetric, -1 to the power L or -1 to the power 0 equal to +1, which means that these 2 cases, the color and space component and the flavor and space component, they are like this, antisymmetric, and this is symmetric, so that the overall wave function is antisymmetric. So these are the two ways to form totally symmetric wave functions from spin and isospin. How? There are basically 2 ways to do that. First, combine totally symmetric spin and isospin wave functions. This is symmetric for this case here I have shown. And number 2 is combine mixed symmetry spin and mixed symmetry isospin states, like this, MS here. However, it is not sufficient since these combinations have no definite symmetry under 1, 3. But it is not also, I am not showing you, but it can be shown that this normalized linear combination, this one is totally symmetric under all these 3 cases. Thus, the total spin up proton flavor spin state function is this thing. Okay, now for your case, I have shown here the exact calculation. This thing, you see, the case here, which I have just talked about, and I am now writing down the various components from the various parts. That means this thing, I have already, I am using the results from this spin case and the flavors case here. I am using these results in this case here, and I am finally getting this proton, this case here. Now for the case of spin up, I have shown here. Similarly, you can do this for the case of spin down, and also if you replace u with d, you can get the neutron state up wave function. You can do this yourself. You just have to, for this, start from this case proton up, and you replace 1u with 1d, and you will arrive at this case here. And now similarly, for the case of this delta plus spin down, you get the two symmetry components. You multiply those two components and you get the final result like this. So with this, I have talked about the UD sector baryon decouplet here, this one. Or what about the others where S is there? For this, we need one extra component, or the third component, the S quantum number, and so we will talk about this in the next lecture when we will talk about SU3 instead of SU2. So SU2 is good enough for this UD sector only, and similarly I have talked about the NP case, which is the spin half octet, where I have used the mixed symmetry spin wave functions to derive their flavor spin component. Fine. So with this, now let's move forward to the consideration of antiquarks, so that we can discuss about the mesons of the UD sector. Now we know that a meson is a bound state of quark and antiquark. So till now we have been talking about quarks only. You see this thing. So let me now represent the antiquark like this here. Now you must be wondering how you do that. Well, this ordering and the minus sign here in this antiquark doublet ensures that antiquarks and quarks transform in the same way. You can check this yourself. I'm not going into the details, and this is necessary also if you want the physical predictions to be invariant under this UD and U bar D bar symmetry. Fine. So with this, let us now again do the same old trick that we have been doing. Let us consider the effect of the ladder operators on the antiquark isospin states. Here I have done this simple case, and so you see the ladder operator on the antiparticle isospin states are this. You can compare this with the previous scenario. And so here I have written down the construction for the light UD mesons. Just 1 plus 1, 1 minus 1. This is the case, and so you finally, using this simple algebra, you get this 1 0 state. Now from this orthogonality gives, this is very simple, this plus minus sign and this is plus sign, you get the 0 0 state. Now to show that the state obtained from orthogonality with 1 0 is a singlet, we have to use the ladder operator. And remember that a singlet state is a dead end, sits in the one-dimensional axis representation, it is just alone. So if you apply t plus or t minus, it will yield 0. There is no other state to move forward to, right? And thus we have this complete identification of the flavor state functions. So, and these three are the isospin triplet 1 1. Yeah, you see the 1, and this is the isospin singlet. Fine. And so what do we get? Basically what we are getting here is the meson flavor state function for the pi and eta mesons, right? And this is very important also for examinations. So to summarize, this is what we have done: 2 cross 2 bar obtaining 3 plus 1. And this is just to end the talk. This is just the isospin representation of quark doublet, and this is the same for the antiquark doublet. And so we have achieved the 2 aims that we have been wishing to talk about. That means construction of this baryon flavor state function and the construction of pi and flavor state function. And in the next talk, I'll talk about the hadrons in the UD sector. Okay.